The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. Welcome to Coffee with Caleffi. We're delighted to have John Siegenthaler with us today doing the presentation. Hot topic and a timely topic, I think, on buffer tanks and using thermal buffering in systems. So Siggy's going to run through a couple housekeeping slides here in the beginning, and we're going to get right in the material. If you have to leave partway through or something like that, we'll get it to you. Hydronic 17 is at the printer as we speak. I believe Mary put the PDF on the website yesterday, so a lot of the information that Siggy's going to cover today is in Hydronic 17. If you aren't getting Hydronics mailed to you, just go to our website and sign up, and we'll make sure that we get you on the list that you get the upcoming issues. 18 we're looking at. I think water quality, Siggy, is what we're going to look at next.
Yes.
So that'll be another good one. But as always, any information that you want us to cover, let us know, and we'll try and get an Hydronics out. So, gosh, let's jump right into it. I know I got a lot to cover, and we tend to run long sometimes. So let's get into it.
Thanks, Hot Rod. Good to be with you all today. We do have a lot to cover. Thermal storage in hydronic systems is a broad topic. Hydronic 17 is a pretty broad issue. It covers a lot of things that we won't have time to get into, but think of today's webinar as a sampling of the content that's in there. You can see some of the topics here that we're going to be looking at here. Some of the basic physics that's associated with using water for thermal storage. And then we're going to start looking at applications, buffering on-off boilers, buffering modulating boilers, and some unique applications like biomass boiler systems. We're doing quite a bit of work now with pellet-fired boiler systems, and storage is a very critical issue there. Okay. Not sure what the noise is there, but I'll keep going.
Yeah, somebody's got their mic open, I think. Sorry.
Okay, no problem. Water. Water is really one of the best things on Earth for storing heat. And just to show that, I'm going to do a comparison between water and concrete. And the two red rectangles that you see over here, these are comparing what we call heat capacity. That is the amount of heat that it takes to raise a given volume of a substance 1 degree Fahrenheit. And in English units, how many BTUs would be required to raise a cubic foot of a material 1 degree Fahrenheit? For water, it's about 62 BTUs per cubic foot per degree Fahrenheit, and roughly half that for concrete. And I've had questions over the years, wouldn't concrete be a better material to store heat in compared to water? And actually, from a volume standpoint, it shows you that water has about twice the heat storage capacity of concrete on a volume basis. So water is a good material. Another question that will come up occasionally, what about sand as a storage material? And actually, if you compare the heat capacity of sand, you can see it's quite a bit lower than either concrete and substantially lower than water. So yeah, sand can store some heat, but it's not in the same league as water is when it comes to heat storage. And I threw this slide in that you see in the lower left corner here. Some of you, if you go back to the early solar days, may remember rock bins. The idea of building a fairly large container, probably in your basement, and filling it up with cobblestones and then blowing air from solar collectors, air-based collectors, through those rocks when the sun is out, heating the rocks up, and then blowing air through the rocks and bringing that air through ducting up into the living space. I don't think anybody's doing that anymore. What do you think, Hot Rod?
I haven't seen it for a while.
It's not too appealing when you think about that air going through those rocks and then going in your lungs. So I'm going to tell you to stick with water when it comes to thermal storage, and obviously that's a great tie-in with a hydronic system. So what do we use thermal storage for? There's quite a few things. We're going to look at buffering boilers, again, short cycling. Short cycling is this idea that the heat source, be it a boiler or a heat pump, is on for a unacceptably short period of time. Maybe it's on for a minute, minute and a half, 2 minutes, and then it's off. And over the course of a heating season, that can be tens of thousands of start-stop cycles. It's going to take its toll on the equipment in that boiler, things like hot surface igniters or contactors in a heat pump. So we want to protect against short cycling, both with on-off boilers and also with modulating boilers. Thermal storage also, it lets the rate that we can deliver heat to the load be substantially different from the rate that the heat source produces heat. It can, in a case of a transient load where we need a lot of heat in a short period of time, our limitation is just how fast we can bring the heat from storage to the load. It's not how fast our heat source can generate heat over a short period of time. We can also use the same thermal mass that buffers space heating to buffer domestic water heating loads. And we're going to show you some details for that. Now, there's ancillary benefits to thermal storage. A properly configured thermal storage tank can also provide hydraulic separation when we have multiple circulators in a system, and we don't want those circulators to interfere with each other. We'll show you some schematics on at least 2 different ways you can set up a thermal storage tank so that it also serves as a hydraulic separator. We can take advantage of favorable time of use electrical rates. Some of you may live in utility areas that have off-peak electric available at night for perhaps half the cost or even a third of the cost of what the electrical rates are during the day. Again, we can run those heating elements when the electricity is cheap. In a sense, we're buying electricity when it's on sale from the utility, storing it in the thermal storage tank. If you're working with combined heat and power systems, again, thermal storage is a critical part of these systems. They tend to work best when the generator is running flat out hour after hour. And oftentimes we don't have a thermal load that can accept the heat of rejection of that generator set at the same rate that that heat is being produced. So we need to park that heat in storage. Now, the physics of storing heat. The equations are pretty straightforward. The amount of heat that a given volume of water will store is calculated based on the volume, and in this case will be in gallons for V, and the temperature change of the water. So if we know a temperature change and we know the volume of water, we can just plug some numbers into this formula and come up with the amount of heat that has been put into storage or taken out of storage. And just as an example down here, let's say we start with 500 gallons of water at room temperature, 70 degrees, and we want to know how much heat has been added to take that same 500 gallons up to a uniform 180 degrees Fahrenheit. And again, a little bit of simplification here. We're saying this tank is completely uniform at 70 degrees, as well as this tank here. So we just plug the numbers into the formula. We have 500 gallons of water. It changed from 70 to 180. So you can see that's almost 500,000 BTUs of storage. Now, think about that in the context of a house where you might have a design heating load of perhaps 30,000, 35,000 BTUs per hour. That's several hours worth of heat in that tank of water. Now, the same formula will work when we're taking heat out. Again, it would be the volume times the temperature change. So if we were to take 500 gallons of water at room temperature, 70 degrees, and run it through a chiller and bring it down to a uniform 40 degree Fahrenheit, we would have extracted, according to our formula, 125,000 BTUs. So this formula is it's an easy formula to work with, and it works both adding heat and taking heat out of water. Okay, now, next topic. We're going to look at 2 different configurations for thermal storage tanks. And you'll see that there are some minor differences, and many tanks, such as the Thermocon tank from Caleffi, they have the connections that allow you to set it up either way. So let's do a comparison, what we call a 2-pipe configuration versus a 4-pipe configuration. The 4-pipe configuration we're looking at here on the left, this is the classic way to set up a thermal storage tank. This has been used in many systems, and it works. And if we look at the energy flow in this situation, we're starting with some kind of a heat source. It could be a biomass boiler, it could be any kind of a heat source. We're putting all the heat that is being produced by that heat source into storage, or at least passing it through the thermal storage, and then extracting it from thermal storage and sending it off to the load. All right, so it's kind of a sequential or series relationship there between heat generation, thermal storage, and load. Now, in a two-pipe configuration, we have different situation here. You notice that in a two-pipe configuration, we only have two pipes that directly connect to the tank. We've got one going in upper sidewall, another one coming out lower sidewall, and then we have two T's that are fairly close to the tank, and that is an important detail. For hydraulic separation, we want to keep this T here in the red line as well as this T down here in the blue line. We're going to keep those close to the tank. We want to have minimal pressure drop from that T down through the tank and back to this lower T. But you can see the difference here is the load takes off before the tank. So we have heat being generated from a heat source. Some of that heat can flow up to the heating load. You can see that actually better up above here. There's a possibility that if the heat source is generating heat at the same rate that the load is requiring heat, this would be the path that heat would flow. None of the heat has to go into storage. That's kind of a unique detail that is different from over here. In this case, we're passing all our heat through storage. Okay? If we had a situation where the heating load was, let's say, half of the rate of the heat source generation rate, well, half of that heat source generation would go to the load, the other half would flow into storage. All right? Let's say that the heat source is off and we have a very small heating load. At that point, we would be flowing backwards from thermal storage going to the heating load. And we can take heat back from the upper portion of this tank, go off to our load, and then return right back to the tank. So it's a nice configuration. I tend to like this two-pipe configuration. One of the reasons I like it is it reduces the flow velocity of the water going into the tank when we have a situation where the load is on and the heat source is on at the same time. And just to show you a comparison, let's start over here with the two-pipe configuration on the left. We've got 10 gallons per minute of flow coming in from our heat source. Let's say our load requires 8 gallons per minute. Well, that leaves 2 gallons per minute to flow over into the tank and ultimately would flow downward through the tank and back out here. It recombined with the 8 gallons per minute returning from the load, and 10 GPM would go back to the tank. Now, if we had the same configuration or the same scenario as far as flow rates, but we used a 4-pipe configuration over here on the right, you can see that it would be 10 gallons per minute going in the tank. 8 would pass through the upper portion of the tank and go off to the load. We'd have the same 2 GPM going downward through the tank, and then the flow rates would recombine at the bottom. The difference here is right up here at the top. We're getting more flow into the tank. That implies higher local flow velocities inside the tank. Anytime we have higher velocities in a tank, we tend to get currents in a tank that will tend to stir the tank. And one of the important concepts that we're going to look at in a few minutes, we don't want to do that. We want to maintain stratification in the storage tank. It is more useful in a tank when that tank is properly stratified. So we want to get away from piping geometries that would cause any kind of, especially vertical flow velocities, excessive vertical flow velocities in a tank, because ultimately that will tend to stir the tank. And I'll show you some examples of some installations where that's occurred. Let's talk about buffer tanks now for on-off heat sources. So these could include boilers such as an oil-fired boiler or perhaps a dry-based gas-fired boiler, a heat pump, non-modulating heat pump. All right. So let's take a scenario. Here's a possible piping schematic where we've got a low-mass boiler. Let's assume that this represents a copper tube boiler, relatively low metal content and water content compared to, let's say, a cast iron boiler. And we come out of that boiler, we have a diverter valve. We can either go to the left through an indirect water heater and then back through to the boiler, or if we have a call for space heating, we go to the right. And you can see over here we've got a lot of zoning going on. But the zones that you see there in gray, let's assume those zones are off. So let's put some numbers to this scenario. Let's say we have a load of 2,500 BTUs per hour requiring heat, but our on-off heat source, this boiler, is either zero output when it's off or 75,000 BTUs per hour when it's on. All right? So we're generating heat at 75,000 BTUs per hour, but we're only taking heat away to the load at 25,000. So we have excess heat production, 72,500 BTUs per hour. All right? Now let's assume that the water that's in this low mass boiler and the metal content, as well as the water that's in this one zone distribution system. In other words, if you look at this path here that I'm tracing out with the cursor, let's assume that that's equivalent to 5 gallons of water. It has the thermal mass equivalent of 5 gallons of water. And let's assume that the controller on the boiler is set for a 20-degree temperature differential. So it has some set point. I'll pick a number. Let's say it's 170 degrees Fahrenheit. When it drops down to 20 degrees below that set point, the burner goes on again, a 20-degree swing. Well, if we calculate how long will that boiler be able to operate when there's an excess heat production of 72,500 BTUs per hour, and here's our formula, 8.33 times volume, 5 gallons of water, times a delta T of 20, you solve that, it's 42 seconds. In other words, 42 seconds of operation of that boiler would take that high limit controller up through a 20-degree swing, and it's going to shut off the burner at that point. And that would definitely constitute a short cycle. There's no formal definition that I'm aware of for a short cycle, but I'd like to throw a number out for your consideration. It's 10 minutes. I think if you think about it, most boilers, heat pumps, and so forth will have a reasonable life if they can operate for a minimum on time, 10 minutes, perhaps longer under stronger, higher load conditions. But we don't want to have boiler cycling on a 42-second basis. So it shows you the problem. So here's a solution. This could be a thermocon tank piped in, and you can see it's a two-pipe configuration. We would just have plugs in the other connections, or we may be using these connections for something else, but from the standpoint of buffering the heating load, it's a two-pipe tank, and our load takes off just upstream of the tank, and that would be a good setup. Now, in this system, again, this diverter valve, it either allows that flow to go this way over to the space heating load or the tank, or the diverter valve allows it to go to the indirect water heater. We would probably set a system like this up for priority domestic hot water. So if we got a simultaneous call for domestic water heating and space heating, we would go to domestic water heating. But the nice thing about this system is even while the boiler is sending heat to the domestic water load, we can still extract heat. We would just reverse this arrow here. We still extract heat, send it off through our one active circuit. It would come back and right back through the tank. So even though we have priority domestic water heating, our tank can still supply energy to that heating load. Okay. Here's another system set up with a 4-pipe configuration. This would probably be a little more, I guess I'd call it classical in the sense that the 4-pipe buffer configuration is probably better known. But again, we would have slightly higher flow velocities in the upper and lower portion of that tank and perhaps get a little more mixing compared to the 2-pipe. If you want to calculate the size of a buffer tank, we need to know a few things. We need to know what is the output of the heat source. Now, this is, again, for an on-off heat source. So if we know the rated heat output of the heat source, that would be this QHS here. Q load would be any load that we know is on when the heat source is on. Now, some heat sources won't fire unless, or they won't operate unless there's some kind of a load calling for heat. It depends on how your system controls are set up. The conservative thing would be to treat Q sub load as 0. Let's assume that there's no simultaneous heating load, that all the heat production from the heat source is going into thermal storage. And then we divide by 500, and we divide by the temperature swing that we are going to allow that buffer tank to go through. And if you're trying to decide that, again, there is no standard on this. I would suggest something from 40 degrees Fahrenheit on up. Basically, the wider the delta T, you can see it in the math here, if the larger this gets, the smaller V, the volume of the buffer tank gets. So let's do an example. Let's say we have a 75,000 non-modulating boiler, and we want to set it up for a minimum on cycle of 10 minutes. And, oh, I'm sorry, I skipped T. We had small t over here is the minimum on time that we want that heat source to operate at. Let's assume we have a concurrent heating load, a small towel warming radiator at 2,000 BTUs per hour, and our controls on the buffer tank are going to turn on the heat source when it drops down to 120 degrees Fahrenheit, turn it off when it goes up to 180. So we have a delta T of 60. So we put the numbers in the formula, calculate it out, and you can see it's not a large tank, just under a 25-gallon tank, and there are buffer tanks available. Caleffi has a thermocon at 25 gallons that could be appropriate for a situation like this. Okay. Again, anything that widens the delta T or lengthens, widening the delta T is going to reduce the volume of the buffer tank, and also anything that lengthens the on time of the boiler, that's going to increase the size of the buffer tank. Now, if it's a modulating boiler, the only thing that changes in the formula is the minimum heat output rate of the boiler. We're assuming that the boiler can go down to some minimum rate and remain stable, have stable combustion conditions at that rate, as opposed to an on-off heat source which always has to operate at that peak output. So we'll do another quick example. Let's say, again, it's a 75,000 BTU per hour boiler, same peak output, but it has a 5-to-1 turn-down ratio, which implies it can go down to 1/5 of its rated output. We're going to shoot for a minimum burner on cycle of 15 minutes. We're going to assume that our towel warmer releases 2,000 BTUs per hour. And I'm purposely putting in a narrower delta T here. We're going to start that burner when we drop down to 110 in the buffer tank. We're going to turn it off when we get up to 130, so we only have a 20-degree swing. Put the numbers in a formula, and you can see it's about a 20-gallon tank. So again, there are applications where smaller buffer tanks make sense, and a modulating boiler in a small residential application is a good example of that. Okay. Let me show you another concept here. I call this concept of a single thermal mass combi system. And the word combi system means the system is going to supply both space heating and domestic hot water. How can we do that using a single tank? Well, let's start with a more typical scenario. Let's say we're going to use a two-tank system. We have a dedicated indirect water heater here. All right. We also have a thermal mass, a small buffer tank that is perhaps a 25-gallon buffer tank matching up with our previous example. And over here on the right, we've got a variable speed circulator. We're going off to a manifold distribution system serving panel rads with thermostatic radiator valve. So it's a nice system, all right? But we have two tanks involved. That means more space. Well, obviously that means more cost if we have to buy two tanks. We have more standby heat loss, which is something you want to be aware of anytime you're dealing with thermal storage. I'd like to think of thermal storage tanks as big thermos bottles. I was always impressed by how you could put hot coffee in a thermos bottle at 6 a.m. and at 6 p.m. open that up and still have steaming hot coffee. So think of the thermal storage tanks that you create as thermos bottles and be very generous with your insulation. We're going to have more heat loss, and also we're going to have a bigger footprint in that mechanical room. So how could we provide buffering for space heating as well as domestic water heating and do it with a single tank? Well, there's a lot of systems in Europe that do this. If you have a chance to take a look at some of these, you know, I put a few of them in here just as a sample. If you walk around trade shows in Europe or today, get on the web and take a look at some of their sites, one of the things you'll notice is oftentimes you'll see an appliance like this, which, if it didn't have the transparent windows in it so that you could see what's inside, and if you didn't know you were at a heating trade show, and if you stuck a handle on it right here, you'd probably think it's some kind of a small refrigerator. Very, very clean industrial design, but down at the bottom you'll see there's actually a thermal storage tank, and there's a coil inside the tank. It's been cut away here so you can see it. Here's another one from a different company. Again, you'll see an insulated small tank, probably on the order of 20 to 25 gallons in the bottom of these appliances. And the concept is shown over here. What they're doing is they're basically using a modulating, condensing heat exchanger, as we would have in a wall-hung boiler, and they're sending that heat down into this insulated tank. The tank then connects out to a space heating distribution system, but it also has a coil heat exchanger. Typically, it's a corrugated stainless steel coil, generously sized, so there's a lot of surface area. Some of you may remember the old boilers with tankless coil water heaters, where the boiler always maintained a higher temperature, even during a hot summer day. Might have a boiler sitting at 160 degrees, because cold water would come in and would make one pass through that coil and then go off to the load. Well, think of this as a tankless water heater on steroids. This is a much bigger coil, so we don't have to have the water in the tank as hot. Obviously, if we want, let's say, 120-degree water to the taps, we probably are going to have to maintain this water in this tank at maybe 125 to 130 degrees Fahrenheit. But we only have a single thermal mass there that is buffering space heating, as well as providing an instantaneous source of heat through that coil heat exchanger for domestic water heating. Okay. Here's one way that you could set something up like that. This tank is actually buffering space heating, and it's also providing domestic water. I set this up around a pellet-fired boiler. With a pellet-fired boiler, we have to have boiler protection. We have to protect that boiler against sustained flue gas condensation. So that's what the mixing valve is here. This is basically to allow that circuit to warm up as quickly as possible, get the boiler's heat exchanger above the dew point of the flue gases so we don't cause corrosion inside the boiler or the venting system. And then you recognize that if you just kind of cover up this, I'll talk about that in a minute. This is a two-pipe buffer tank. This could be a thermocon tank set up. We've got an auxiliary boiler tied in just into the upper portion of the tank. So the auxiliary boiler can basically heat this upper portion of the tank. And we've got zoning going on. Now, I'm showing 4 zones, but maybe we have 8 zones here. Let's say we have a lot of zoning going on. Anytime we see a lot of zoning going on, we want to think about buffering, because the finer we divide up that distribution system into zones, the more likely it is that we could have a single small zone that is substantially less heat demand compared to what our heat source is capable of delivering. Even a ModCon boiler has limitations. If one zone here was 2,000 BTU per hour and ModCon can only go down to 10, that still means that the ModCon is producing heat 5 times faster than the load is requiring. So we're going to use the upper portion of the thermocon tank for the buffering. What we have over on the right is a on-demand domestic water heating assembly, and it's a pretty simple idea. We have a heat exchanger. This would be typically a stainless steel braze plate heat exchanger. We have a flow switch. When somebody opens a tap for hot water, the flow switch contacts close. Through a relay, we turn on this circulator. We bring hot water, and this white line just represents on the thermocon tank. We've actually got 3 connections up on the high sidewall. So rather than tee in here, we can just run a separate pipe in. We take hot water from the top of the tank, go down through the primary side of the heat exchanger, go back into the tank, and simultaneously our cold domestic water makes a pass through the secondary side of the heat exchanger, comes out. We'll put in a anti-scald rated tempering valve and then off to our load. So what we're doing with this is we're actually using the thermal mass of the thermocon tank for buffering both the space heating load as well as providing domestic hot water. And the heat sources, basically this would be the priority heat source. The auxiliary heat source, the ModCon boiler, would just come on if and when the pellet boiler cannot keep up with the load, or perhaps it's maybe in the summer you choose not to fire the pellet fired boiler, in which case the ModCon boiler could take over. So it's a nice concept. It's relatively simple piping there. Let's switch over. Let's talk about stratification. I mentioned earlier that stratification is important, and I want to show you why that's important. And to do that, I want to introduce you to something. Some of you have probably heard of this concept. It's called exergy. Not energy, but exergy. And what exergy stands for is what I call the quality of the heat. Basically, the higher the temperature the heat source is, the higher its exergy, the more useful it is. And just to kind of illustrate that, here we have a tank that is stratified. We have 120-degree water in the upper portion of the tank. We have 100-degree water in the lower portion of the tank. Let's assume that we had kind of a linear gradient from top to bottom in the tank. So our average tank temperature here would be about 115 degrees Fahrenheit. Now, if I were to stir that tank up without adding any energy to it, I'd have this picture over here. And I can show you a couple ways to stir up a tank. One is to have a vertical flow jet by creating a vertical inlet pipe in the top of the tank. And these red arrows would represent hot water that's basically being pushed down. And you kind of visualize this. Imagine taking a garden hose and just putting it down into the top of a 5-gallon pail filled with water. You know you're going to get a stirring action inside that pail, and you would get something similar to that inside the tank. So we don't want to do this. Neither do we want to do this, a return pipe that comes up into the bottom of the tank. And this is a common error, and I'll show you a couple systems. But however we've stirred that tank up, we've got the tank at a uniform temperature of 110 degrees Fahrenheit. Now, both tanks, in theory, have the same amount of heat in them. If we said the average temperature over here was 115, and we had a linear temperature gradient top to bottom, we would have the same situation. 115. We'd have 110 here. I'm sorry. My average would be 110, not 115. 120 down to 100. Average of 110. So let me ask the question now. If we had a load that required 115-degree water, my thinking got ahead of my mouth here. If we had a load that required 115-degree water, which tank could supply it? And the answer is this tank could. We have 120-degree water here. How about if we had a load that required 111-degree water? Which tank could supply it? Again, the tank on the left could supply it. Even though we have the same amount of energy over here, the quality or the exergy of that energy has been reduced by the fact that we've essentially destroyed stratification. So always think in terms of piping details and tank geometries that help preserve stratification in a tank, and stay away from these vertical flow jets. And here's just another slide that kind of shows that. We want to stay away from topside vertical inlets that create a downward jet. We want to stay away from bottom side vertical inlets that create a jet. Now, over here I'm showing a stratified tank, and you notice one of the internal details that has helped create that, we still have this bottom inlet connection, but we've put some type of a flow diffuser in there. And there's a lot of different potential designs. This shows a plate that has been welded into that tank, and there's an annular space out here. The basic idea is the incoming flow would impinge on that plate, it would spread out to the side, and depending on the space that we have out here, we would have a greatly reduced vertical flow velocity as that flow finally moves up into the volume of the tank. Up here at the top, it is fine to take heat out of the tank, to take flow out of the top of the tank, because we're not creating localized high velocities with that, especially if we're just 2 or 3 inches away from that inlet, our velocities are still relatively low. So basically stay away from this and stay away from that. Now, here's a tank. This is a 500-gallon ASME pressure-rated tank that's installed as part of a large commercial pellet boiler system we had a chance to look at recently. And you'll see there's various pipes connected to it. And it's not obvious, I suppose, in looking at that photo what's wrong, but I'm going to give you a hint. We're going to look at this pipe down here in the lower right-hand corner, and there's the flow path. The flow comes back from the building, and here's another photo that shows the underside of that tank. Just lay down on the floor and look under that tank. We have that 2.5-inch pipe coming in, and this is a T, but the side port of the T ends here. We've got a drain and a pressure gauge. So the flow goes right straight up into the bottom of that tank. And if you look at this photo carefully, you see there's thermocouples on this tank. This is part of a research system at a university. And one of the initial findings is that we can't get any stratification to form in this tank. And we trace that back to what's going on with this vertical flow jet. So again, that's this situation right here. I'll show you one other scenario. This is a drawing that we had a chance to review. This is, again, a large commercial pellet boiler system, a 1.7 million BTU per hour system. And just looking around at some of the notes, I noticed this note down here. And that note says, essentially, you may or may not be able to read it, that this pump is moving 180 gallons per minute of flow down through this 3-inch pipe. And if you follow where that pipe goes, it basically goes into the bottom of this tank, as well as the bottom of that tank and the bottom of this tank. In other words, the flow divides up like this, 60 gallons per minute going vertically upward into the bottom of each of these 3 tanks. Now, these are 600-gallon tanks. They're roughly about 6 or 6.5 feet tall. Imagine a 60-gallon per minute flow straight up into a container that's 6 feet tall. You're going to get a strong component, mixing component. So fortunately, this was caught at the design phase, and these tanks have been modified before. They're actually fabricated. And the interesting thing here, there's 3 different flow inlet diffuser designs that are being used, and ultimately those will be studied to see which of those inlet diffuser designs is most effective in helping preserve stratification. So again, be careful of vertical flow jets. Let's talk about multiple tank arrays. The thing you want to be aware of when you're going to multiple smaller tanks versus a larger tank is surface to volume ratio. Obviously, if we put enough smaller tanks in, we can create sufficient volume, but that volume is now in containers that have substantially more surface area. So if we calculate a ratio of the surface area of the tank to the volume of the tank, we have a basis of comparison. Anything that reduces the surface to volume ratio is beneficial. And if you think back to some of your geometry, you probably remember what's the 3-dimensional shape that has the lowest surface to volume ratio? And the answer is a sphere or a ball has the lowest surface to volume ratio. And very rarely you will see a spherical tank. They're used with cryogenic fluids because you have such an extreme delta T there that it's worth the cost to fabricate a spherical storage vessel to minimize heat loss. But spherical storage vessels are just not cost effective for HVAC applications. So with cylinders, we're going to compare it. And what I did here is I compared 4 tanks at 119 gallons each to a single 500-gallon tank, and I assumed cylinders, just to keep the math simple, I assumed flat ends. And we calculated a surface to volume ratio. And as a quick comparison, the 4 smaller tanks here have a surface to volume ratio that's about 61% higher than the 500-gallon tank. So when would you use the smaller tanks versus the larger tank? Well, obviously access. You may not be able to get a 500-gallon tank through, let's say, a 36-inch wide door in an existing mechanical room, or into an elevator or down a stairs or something like this. You'd have to go to the smaller tanks. But when you have a situation where you don't have the spatial constraints or the logistic constraints of moving the tank in, generally speaking, larger tanks are going to have better surface to volume ratios than smaller tanks are. Okay? Now, if you are using smaller tanks, like let's say we want to use 3 thermocon tanks, there's several different ways we can pipe them. This is kind of a unique strategy. This is, I call this a hybrid parallel series. These tanks are sort of in series with each other and also sort of in parallel if you look at them. It's actually a variation of what we called the two-pipe configuration earlier. We have a heat source putting hot water flow in here. Here's our load taking off. Our load return comes back down here. So the points A and B here are set up essentially in a reverse return arrangement to try to balance the flow. In theory, the stratification in all three tanks should be identical. There might be very small variations in that, but I don't feel those variations will be significant. And it really requires you to have short connections here. The shorter these connections are between the tanks, the closer this approximates a single large tank. But from a practical standpoint, we have to think how short can those be and still get these tanks to line up. And if you think about these tanks, I mean, there could be very minor variations in how these connections are welded into the tanks. There could also be variations in the flatness of the surface they're resting on. So to try to connect these with rigid pipe, especially large diameter, like 2-inch or larger rigid pipe, is going to be very difficult. So a short, flexible connector is a good option. Here's an example. Here's a photo that Hot Rod put together for us. It's a short connection. It's roughly about a 12-inch length. That's a 2-inch pipe size connection. And you can see that there's basically a nipple into each tank and then a connection in between there. So that allows you to have slight misalignment of the fittings, but still put these tanks together. And obviously, when you're done with the piping, you'd want to put some insulation on that. Okay, temperature stacking. This is a kind of a unique strategy. I'll try to go through it quickly. When we have a pellet-fired boiler, one of the things we really want to do with a pellet-fired boiler, and this would apply to a wood chip boiler as well, we want to keep that boiler operating for a nice long cycle. Think multiple hours. So we're going to turn on that boiler based on a condition in the buffer tank, and once we turn that pellet boiler on, we're going to let it run until we basically fill this tank up with significantly higher temperature water. We might turn the pellet boiler on when a sensor, let's say at the midpoint of the tank, gets down to about maybe 120 degrees Fahrenheit. If you have a building with a low temperature distribution system, the lower the water temperature that can still heat the building, the better, because it allows us to drain the storage tank to lower temperatures, and that gives us a wider temperature swing on the tank. So that's our on condition. And then our off condition is going to be when the bottom of the tank, or a sensor close to the bottom of the tank, gets up to a fairly high temperature. The way we're going to do this is we're going to keep track of what's called the thermocline in the tank. Thermocline is basically the region between the hotter water at the top and the cooler water at the bottom. So over here on the left, if we have a tank that's essentially at rest and stratified, hot water at the top, cool water at the bottom, our thermocline is wider. Once we start a load and we start to take flow out of the top of the tank, the thermocline is going to tend to tighten up a little bit, and it's also, think of this tank as basically filling from the bottom up with cool water. The thermocline is rising through the tank, and we can use that movement of the thermocline in combination with sensor placement to provide our on signal for the pellet boiler as well as our off signal. Here's our on signal. Again, this could be a thermocon tank. We have 2 or 3 connections up here at the top that you could thread a well into. And you can see that could be a long temperature sensing well. So we could place the sensor vertically at different heights depending on what our criteria are. But let's say we have a sensor at roughly 60% of the height of the tank, and when that sensor gets down to 120 degrees or less, we're going to turn on the pellet-fired boiler. Okay? So now we're putting heat into the tank, all right? And we're going to continue putting heat into the tank until we get this situation. Now, we've installed another temperature sensor near the bottom of the tank. It doesn't have to be right at the bottom. It could be one of the lower sidewall connections on a thermocon tank. But notice what our off condition is here. Our off condition is when that sensor reaches 180 degrees Fahrenheit. So that's a wide temperature swing on the tank. And what this does is it prolongs the operating duration of the pellet on cycle, the pellet boiler on cycle. And that improves efficiency, and it also reduces the emissions coming from it. So, it's kind of a unique strategy. I ran into this a couple of years ago looking at controls from a European manufacturer for pellet-fired boilers. And at first I wasn't quite sure what they were doing, but think it through and it makes a lot of sense. I don't want to take a lot of time to explain this, but you can create this strategy using a two-stage set point controller. You can also do it using a two-stage reset controller. Some pellet-fired boilers include the control logic to do this right in their internal controller. So you don't need to create any kind of external control logic to do this. But this combination of a two-stage set point controller and a couple relays basically allows you to have two different set points, one for an on condition and one for an off condition. If you want to combine it with an auxiliary boiler, we can put another sensor up near the top. And notice we're only firing the auxiliary boiler once our tank is almost depleted of hot water. We're trying to hold off on the firing of that boiler as long as possible, especially if the pellet boiler is starting to put heat back into the tank again. So we could set up some condition at which we'll call it a last resort condition where we do go ahead and fire the auxiliary boiler. In this case, I'm going to wait until this upper tank sensor drops down to 115. This is assuming the load, by the way, needs 120 degree water. So I've cheated a little bit. I put a 5 degree differential in there. And then we're going to keep that auxiliary boiler going until that upper sensor gets to 130. And all that requires is the addition of one more single stage set point control to our control logic here. So again, get the PDF file for the slides and study this at a little more length, and I think you'll find it's kind of an interesting control condition here. Again, here's a system we looked at, or something pretty close to what we looked at earlier, with a pellet boiler, auxiliary boiler, and over here's the temperature scales that show both the pellet boiler on and off condition. Again, it's on at 120 at this sensor. In this case, it's off at 170 at the lower sensor. That's the pellet boiler. The auxiliary boiler is basically on at 115 and off at 130 based on the sensor up at the top of the tank. All right, instantaneous domestic water. We looked at this assembly earlier. Raised plate, stainless steel heat exchanger. This could be a standard hydronic circulator, cast iron circulator with a check in it. I'm showing a thermostatically controlled electric tankless water heater as our auxiliary heating device. And the basic idea is this. We open a faucet, we get hot water demand, cold water flows in past our flow switch. The flow switches typically will close at around 0.6 of a gallon per minute. And through a relay, we're going to turn this circulator on. It is important to keep this assembly close to the tank. We don't want to have a lot of piping between the tank and this, because that's going to delay transfer of heat from the tank to the heat exchanger. So imagine we've got this mounted close to the sidewall of the tank. It's only going to be a couple seconds before we have hot water from the upper portion of the tank passing down through the braze plate heat exchanger and back in the tank. And if you've worked with braze plate heat exchangers, you know they have a very fast response time. They have very high surface area to volume ratios. So again, a second or two will be a typical response time on those. So within maybe 4 to 5 seconds, we'll have heated water coming out of the secondary side of the heat exchanger. How hot will it be? Well, it depends on the temperature of this tank. If this tank was 170 degrees at the top, this might be 160 degree water coming out here. Now, it does show flowing through the electric auxiliary heater, but the thermostatic controls in that would be set, let's say, at 120 degrees. The elements will not fire. The water will pass through it, but we're not going to turn on any electrical flow to those elements. So it's just a pass-through. This is a critical component here, this ASS 1017. I'm not sure if that's a current standard or not, but ASSE 1017 or more modern version of that standard for the anti-scald mixing valve. We don't want to send 160-degree water off to somebody's faucet. Okay. Now, if the tank was only at 80 degrees, this water might come in at 50 and it might get preheated up to maybe 70 or 75 degrees. That's where the auxiliary heater would top it off. It is important that this is a thermostatically controlled, because a thermostatically controlled heater will add just the right amount of heat to bring that water from whatever preheat condition we supply it up to a set point. We won't overshoot. Okay? And there's a lot of advantages to this approach. Again, it leverages a single thermal mass. This can also provide space heating. Okay? Fast response time. We have everything outside the tank. We don't have internal coils that could potentially scale up or ultimately fail, in which case we have to replace the tank. We also have very little hot water residing in this system. Once we shut this off, it's really only the heated water that's in the secondary side of the heat exchanger and this piping that's there. And the advantage there is reduced water volume, reduced potential for Legionella. Okay? And somebody asked one, well, what about the power requirement to run the circulator? We actually did a scenario on that. For a typical family of 4, we found that that circulator will run for less than $1 per year. So it's an incidental cost for operating that circulator. Remember, that circulator only operates when there is an actual demand for domestic hot water. And this is a small circulator in a residential application. 30 to 40 watt circulator would work there. Real quick, that's the inside of one of the electric tankless water heaters. I don't want to take a lot of time with this, but I do want to stress thermostatically controlled. I also want to stress make sure that you have a 200 amp service entrance when you're using these. You don't want the lights to dim when you open a faucet. And these do draw a lot of current. You can see a 12 kW unit here, 12 kilowatts. It's not a very large unit. It's maybe 10 inches tall, 5 inches wide. You can hold it in your hand, but when it's operating, it's 50 amps at 240 volts. So it's a pretty strong demand. Remember, you're heating the water instantly, so there's a lot of power flowing into this. You can size up a braze plate heat exchanger pretty quickly with some of the online software that's out there. When you do that, try not to have more than a 10-degree difference between the incoming storage tank temperature and the leaving domestic water temperature. The larger the heat exchanger is, the smaller this approach temperature difference will get. Within reason, I would say 5 to 10 degrees Fahrenheit will work good there. Okay, we talked through this. The operating cost of that circulator, less than $1 per year. Here's how you could set it up for an open tank. If you were using a large unpressurized tank, we could what's called gooseneck piping through the sidewall above the water line. Basically the same detail. You would want to use either a bronze or a stainless steel circulator here because this is an open system. And you want to keep the circulator low so you have some static head on it. The disadvantage of an open system is you have low static pressure on the inlet of circulators. When the water's hot, you come closer to a potential cavitation situation. Okay. Now, if you're using a tankless water heater that has a safety switch that trips out at 140, you might want to use this detail. It adds a second thermostatic valve. What this does is it blends the water temperature down to nothing higher than 130 as it goes into the tankless water heater. Some of these tankless water heaters have a safety switch built in, non-adjustable, set at 140 degrees. They aren't anticipating water coming into them at 150, 160 degrees Fahrenheit. So obviously, if you did send water in at 150, it would trip this switch. This just mixes it down before it hits the tankless water heater, and then the balance of the system is the same detail. Okay, and this is my last slide. This is what I've been working on for the last 3 or 4 years. A new textbook coming out in December. It's called Heating with Renewable Energy. It's going to take hydronics as kind of the envelope, and within the envelope we're going to be looking at solar thermal systems heat pump systems, both air source and water source, and biomass boilers, pellet boilers, wood chip boilers, wood gasification boilers. So that'll be coming out in December. Caleffi, there's a lot of Caleffi hardware in there. They've been a big help in putting this together. And that's my last slide, Hot Rod, so I'm going to turn it back to you.
Yeah, that was some fast talking, and there's a lot more in Hydronics 17 as far as, just covering more piping schematics and more data. We can only get through so much here in, 50 minutes or whatever you did, but thanks for doing that. And I had a sneak preview of that Renewable Energy book, and it's great. If you've seen John's Modern Hydronic Heating book, this is certainly the companion to that, and it's got a lot of updated information in it, so thanks. Certificates, a couple things for housekeeping. Appreciate the questions and as always the support for Caleffi. So you want to hit a couple, Mark, or do you think we should?
Yeah, maybe there's a couple. Real quickly, working backwards from that slide on the instantaneous tankless hot water using electric instantaneous. The question is it suitable to use gas-fired tankless in that application? They typically require a minimum delta T. What's kind of the quick pros and cons of using gas versus electric?
Yeah, I've never set one of these up with gas. I think the response time on gas is going to be quite a bit longer on it, Mark. And you mentioned something there. They do have a minimum delta T that they have to establish before they fire, and it's essentially the limitation on the low end of the firing range that would limit them in this application. The electric. The nice thing about the electric unit, it's essentially 0 to 100% modulation. So let's say we wanted 120-degree water and we had 118-degree preheat water coming from our storage tank. We could trickle just enough wattage into those electric elements to give us the 2-degree boost. And I don't think the gas-fired water heater would even fire under those conditions because of that minimum delta T. So I would stick with the electric for this application.
Okay. Thanks, John. Another question concerning 2-pipe tanks versus 4-pipe. If in addition to storage, you want to do hydraulic separation, is there any configuration that comes to mind where a 2-pipe might work?
Yeah, 2-pipe will definitely work. I'm just flipping back here to a schematic we looked at. This is going to work for hydraulic separation. Now, the key thing with a 2-pipe buffer is to keep the T's that go off to the load as close as possible to the tank. And you can still see that schematic. What we're looking at is the pressure drop from this T, where the load tees off from the, I'll call it the upper tank inlet header, where that load tees off, and then down through the course, the tank itself has very low pressure drop, almost insignificant. So as long as we keep these T's that connect to the load close to the buffer tank, a 2-pipe configuration will still provide hydraulic separation.
Great. While we're on the tank, the glass line tanks, how would you compare them relative to a long-term perspective in light of water chemistry versus, say, perhaps a stainless steel tank or even an unpressurized plastic tank?
Wow. That's going to be tough. I would think that, the glass lining, it certainly doesn't work against you from the standpoint of applying it in a hydronic system. But if it is a true closed-loop hydronic system, theoretically, you don't need the glass lining. Just a carbon steel tank should work. And obviously, steel boilers, cast iron boilers have proven that closed systems, any oxidation initial oxidation that you have is not going to be a continuing process. Again, I'm presupposing everything remains a closed system. If you were going to have an open system and you still wanted to use a tank, like a thermocon tank, the glass lining should protect it. I mean, the glass lining was developed around potable water, fresh water. So in a true closed-loop application, I don't see it as a requirement, but it's not an impediment either. As far as the life on other tanks, tough to say. Some of the EPDM linings that are out there, typically you hear numbers like 15 to 20 years, and then it's a new liner.
One of the things I would add on that, and just a little plug for the thermocon too, is you want a tank like Siggy mentioned earlier that's insulated completely. I know some of the other tanks that are out there, they don't have the 2-inch of foam completely around. Our tanks are foamed on the top and injected foam, so you've got that 2 inches on the top and the bottom and all around it, so you don't have that loss, out the jacketing through a little thin piece of fiberglass or something that they typically use on some of the other tanks. So that's certainly a key, and we're hoping the industry drives us towards maybe 3 to 4 inches of insulation. I know that's a movement over in Europe right now. I think there's a DIN standard, in fact, over there that they have to have about the equivalent of 3 inches of insulation on tanks that are storing heated or chilled water over there. So,
okay.
All right.
Another question, when we're doing space heating, I suppose chilling as well, or cooling, no domestic hot water in the picture. If you're just thinking from a controls standpoint, is it typically better to maintain your buffer tank temperature, always, or based on first demand or some type of setup like that?
Yeah, again, that's a tough one from the. You really got to look at what the load profile looks like. If it's a load where you're expecting a lot of, I'll say, frequent small demands for heating, it may be justified to maintain the buffer tank. Most of the pellet-fired boilers do that. The pellet-fired boilers don't actually, from a control standpoint, most of them do not look at what's happening with the zones. They only see 2 temperature sensors in the tank, an upper temperature sensor and a lower temperature sensor, and their sole control task is to basically, when that upper sensor drops to a certain value, they turn on, and they remain on until the lower sensor gets up to some higher value. They have no idea what's going on with the load. So there's a case where the buffer tank is essentially always being maintained. But that is kind of a special application. A pellet boiler just doesn't turn on and off like a oil boiler or a gas-fired boiler would. If you have a low-mass gas-fired boiler, the only time I'm trying to think of a scenario here where it would make sense to maintain the load, maintain temperature in the storage tank. If it's critical that you recover quickly from a setback, then I would say probably maintain the tank because there's energy in reserve that can quickly move out to the load. If that's not as critical, and especially if it's a smaller buffer tank, maybe 119 gallons or less, I probably wouldn't choose to maintain it, especially if the loads may be off for a day or two, because that's just standby heat loss. And anytime you're converting fuel, high-grade energy into heat, low-grade energy, it's a race against time as far as heat loss from the tank. So there's no universal answer. That you have to look at the loads. You have to look at, the other conditions, criteria that you've got, and then kind of make a decision. Do I want to maintain that tank, or do I just want to put that tank essentially online when there's a demand?
Okay. I have one other question, and it looks like we still got almost a couple hundred folks still on. So since there's an interest, we'll stick. Since we're a little bit over, we'll stick maybe with a question or two. John, you might want to go up to that schematic that had buffered tank with domestic hot water on priority, and then you had a highly zoned system. I think it might have been a 4, or I think you might have used both a 2-pipe and a 4-pipe arrangement as options. It might have been early.
Yeah. Here it is with a 2-pipe.
Oh, okay. Yeah, I guess it's that one. So from if you're not on priority with your hot water and simply treating your domestic hot water as another zone, would you consider placing your buffer tank in a different spot in that design?
Probably not, because actually when you look at this is mandatory priority in the sense that that valve's either going to go indirect or spacing. It can't do both at the same time. So I would stick with this arrangement. And again, I'd look at it from the standpoint that even when the boiler is supplying the indirect water heater, assuming that there's heat in the buffer tank, the space heating load can still remain active, which is kind of the nice thing. It's priority, but at the same time we have energy flowing to space heating at the same time as we have energy flowing to domestic water because we have the buffer tank piped in like this. I mean, the difference between the 2-pipe and then here's the 4-pipe, it's the same scenario. It's really just the internal flow velocities in the tank that would be affected. So I would say either of these schematics would definitely be workable.
Okay. And last question while we're on that slide, in sizing that buffer tank, in addition to the space heating load, you're also going to take in consideration your domestic volume in sizing?
On this particular system?
Mm-hmm.
Probably not, because think of the indirect water heater as essentially the domestic water load essentially is self-buffering just because of the volume of water stored in the tank. It's it's a self-buffering load. So it's actually a good point. You really don't want to, in my opinion, you don't want to heat up a dedicated buffer tank just to provide heat to an indirect water heater, because now you're maintaining 2 tanks and you're going to experience higher standby heat loss. So
good point.
Specifically moving that high mass domestic water load, treat that as self-buffering, and then everything on the space heating side goes through the other buffer tank.
Great. Okay, we have a couple more questions, but they're stratification related and very specific to some schematics, so perhaps we'll just cut right here, and I'll pass it over to you, Bob, for a wrap.
Yeah, well, thanks everybody for tuning in. Again, let us know your questions. We'll get to you here. It might take a couple hours or a day maybe to get to all the questions, but we'll certainly get back to you. And we appreciate your tuning in today and your support. And thanks a lot, Siggy. This was another great presentation. And